So the first talk is by Professor Mairi Sakellariadou. I request Professor Sakellariadou to give her talk. Thank you.
Okay, thank you very much for the invitation. Let me share my screen. Is that okay? Can you see it?
Yes, we can.
Okay, so this is the title of my talk, Gravitational Waves, the Theorist Swiss Knife. So what I would like to try to do is to convince you, if you are not already convinced, that one can use gravitational waves in order to learn a lot, for instance, about astrophysics of compact binaries, about the large-scale structure of the universe, dark matter, processes which took place in the early universe, particle physics models beyond the standard model, modified gravity, and even quantum gravity. So let us start. Here I give you a classification of the nature of the gravitational waves, which can be phase coherent, transient, or persistent, and phase incoherent, again, transient or persistent. Now, for the phase coherent ones, what we try to do, we try to identify them by matched filtering techniques. And for the case of the persistent waves, like when we're searching for continuous waves by spinning neutron stars, these are very hard to be able to disentangle from the instrumental noise. So there is no surprise that all the events that have been discovered by the LIGO-Virgo-Kagra collaboration, you can see here the references where we have the catalogs of these transient events, are nothing else than the gravitational waves which are emitted by compact binaries. So in this kind of talk, I'm going to focus first on the stochastic gravitational wave background, which is defined as the random, non-deterministic phase evolution of gravitational waves coming from sources which are either very far away or they are very weak, and we do not have the perfect instrument to be able to identify them. And then I'm going to move to the transient gravitational waves. I'm going to discuss what has been done so far and which are the implications of a detection or a non-detection, like the case of the stochastic gravitational wave background. So let me start. We all know that the universe is filled with electromagnetic radiation, which is nothing else than the photons of the Big Bang. In addition to that, we expect that the universe is going to be filled by stochastic gravitational wave background, which is generated by events that took place in the very early times of its history. On the top of that, there's going to be a background of gravitational waves, which comes from the incoherent superposition of waves from sources which are either very far away or they're very weak. And as I said before, we still are lacking the perfect instrument that will be able to identify. Then, in terms of gravitational waves, it is proportional to the square of the time derivative of the strain. And they are usually expressed, like all cosmological parameters, in terms of a dimensional quantity, which is this omega GW, which is the energy density of gravitational waves in a logarithmic interval of frequency and normalized by the critical energy density. I hope you can see the cursor. Now, if you consider...
Yes, we can.
Thank you. If we consider the cosmological contribution to the gravitational wave background, so as these perturbations propagate through a universe which is inhomogeneous, the phase of the waves is going to be affected by the metric perturbations. And as a result, these perturbations, these gravitational waves are going to lose any kind of phase coherence which they had when they were emitted or when they entered the horizon. Now, if you take the astrophysical contribution to the gravitational wave background, it has as well no phase coherence. This has been shown in this paper here, that if you take a standard cosmological model, then complete loss of coherence is going to happen at frequencies above 10 to the minus 12 hertz. So if I take the strain in Fourier space and I write it in terms of the amplitude and the phase, since the phase is random, the only quantity that's going to play a role is the amplitude of the gravitational waves. Now, for the first part of the talk, I'm going to consider the standard assumptions, which tell us that the gravitational waves have a spectrum which is isotropic, unpolarized, stationary, and Gaussian, which means that all information is going to be given by the two-point correlator of the strain, and here A and A prime are the two polarizations, where in GR, so we have two polarization modes. Now, the gravitational wave background has not been detected so far, but we expect that it's going to be detected as our tools, as our interferometers are reaching their design sensitivity. So probably we may hope as well in the fourth observing run that we might have them. I mean, wishful thinking, I could say. Now, if you have a single detector, let me indicate it by I, okay? And you write in full space the strain, then it's the signal, then it's going to contribution, the strain, the noise much bigger than strain. So with a single detector, you cannot find the gravitational wave background because the noise is much bigger than the strain. So you have to combine the output of two detectors, I and J, in this way, okay? H is the strain, the noise, F is the frequency. I am in Fourier space. In addition, let me say this to-noise ratio is going to grow slowly with time, goes like the square root of the observing time. So how are we trying to detect the gravitational wave background? We are building this estimator, Cij here, okay, in this way. Si, it is the Fourier transform of the strain time from a detector I, okay, starting at time t. J is my second detector. Gamma Ij is what we call the normalized overlap reduction function. You can see it here for different pairs of interferometers, which actually covers, it just takes into account the geometric factors that are going to take into play when you take the cross correlation of your two detectors. T is the time at which you take the Fourier transform, and this S0 is a normalization, is the spectral shape for a gravitational wave background that it is flat in the energy density. Now, if we assume that the gravitational wave background is isotropic, gas stationary, and unpolarized, then it is fully described by just one quantity, the spectral density SGW, which is related to the energy density I defined before, this dimensionless parameter, like all cosmological parameters, omega GW, in this way. So now, if you assume that the gravitational wave signal and the intrinsic noise are uncorrelated, as you can see here, this estimator I built before gives in the omega GW plus a contribution from the correlated noise between the two detectors. If there is no correlated noise between the two detectors, then this estimator I built before, it is the way to calculate the omega GW. And that's what usually has been done for a long time. But what if this assumption is wrong? What if there is a correlation between the noise of the detectors I and J? And you might wonder when this could be a case. An example are the Schumann resonances, which are global, extremely low frequency peaks in the electromagnetic field of the Earth. So there are these resonances, which are eigenmodes of the conducting spherical cavity, which is formed by the surface of the Earth and by its ionosphere. And you can see that it has this kind of excitations. For instance, the first one is around the circumference of the Earth, which is about 8 Hertz, then you have 20 Hertz, and so on. And if you go to see the power spectrum that you get of your magnetometer near the location of the Virgo in Italy, you see exactly this kind of peaks that are going to arrive. So this, they might contaminate my signal. So if tomorrow I say that I have detected the gravitational wave background, how do I know that is a reaction and there's not a contamination from magnetic noise? So in that case, you are going to have that this estimator, it is going to give you the omega GW plus a magnetic contribution. So a couple of years back, we proposed to look for that. So we assume that the data in the magnetometers, MIJ, MJ, these are the magnetometers at the sites I and J, have a cross-spectral density given in this way, where this gamma IJM is the corresponding of the overlap reduction function I had for my interferometers, here for magnetometers. And then the peaks in the detector strain channels are going to be related to the peaks in the magnetometer, a transfer function, which has a power law kind of form. It depends on a coupling and on these powers. These values we know from the second observing run, and then we know what will be the contributions that we are going to have in our estimator. And this is a method that has consequently been used in the following kind of, at least in the last observing run, and is planned to be used as well in the next observing run of the LIGO Virgo. So in the third observing, because we were able to combine the output of 3 detectors, okay, the twin detectors of LIGO and the one of Virgo. We could build our cross correlation. From there, we could build our, and the result of this exercise, looking as well for the kind of magnetic noise contribution, was that our data are consistent with uncorrelated Gaussian noise. But as the sensitivity of our detector becomes better, then certainly the contribution or the possible contamination of the Schumann resonance may indeed become important. So this is a technique that has to be used always. Now, by the non-detection of gravitational, of the stochastic gravitational wave background, you can still find some kind of important constraints for your theories. How do you do so? There are 2 parameters that you have. So usually, depending on what is the source of the gravitational wave background, the omega GW has a power law form with the value of this power law that depends on what is the source. For instance, if you have inflation or topological defects, that's going to be 0. If you have compact binary correlations, by writing down the quadruple formula, which I will do in a second, you will see that this becomes 2/3. Okay, so depending on what is the value of that, you can put constraint on this parameter, then you go to your theoretical model, you calculate it, and it will depend on some parameters which you are going therefore to constrain. So you the limits of this omega reference for different value of alpha that have been given for the data. So here, for instance, is what I was saying, compact binary correlations. So I'm write down the quadruple formula. The quadruple formula, I'm sorry, here the frequency is new, goes like the frequency, the minus 1/3. And once you go to take the integral for all frequencies, you have this famous 2/3 kind of law. So here in the left kind of panel, we saw the 90% credible bands for a gravitational wave background contribution from binary neutron stars or binary black holes. At the time that this paper came out, we didn't have a kind of confident NSBH kind of detection. That's why you see this upper limit. What about the right-hand band? I considered a binary black hole and a binary neutron star population using the rates which are given by the LIGO Virgo kind of detections. And then I go to calculate a power law spectrum. If it is tangent in one of these curves, which are nothing else than the sensitivity curves of my instrument, then I say that I have detected gravitational wave background at the 2 sigma level. Here, for instance, you see this was the O3, the last term we have. This is the design sensitivity, and this is the A+, even better. And non-detection
Srinath, can you?
Professor Sakellariadou?
Yeah, I was wondering whether the issue is with, yeah, maybe there is a connection which has got disconnected. I'll just, I think the connection to her got disconnected.
Is that okay? Is that okay?
Yeah,
yes,
we got disconnected for a minute. Can you share your screen?
Yeah, I said, do you see my screen?
Not yet. Not yet.
Not yet. I'm sorry for that. Can you see my screen?
Yes.
Yes, we can.
I think I stopped there. I was lost there. Okay, so what I wanted to say is that gravitational waves from compact binaries can give information about the astrophysical models. So here I'm writing down. Slide. The previous slide was that you have seen that.
Yeah. Yes.
Okay, so here I finished by saying that the gravitational wave background from compact binaries, it is really hard to be identified, because easily you can come to that conclusion if you compare it with the one from the cosmic microwave background. It's 10 to the minus 5, here we're 10 to the minus 9. Okay, so there's no wonder why really it's not very simple to get it. So then I would like to say how a detection of gravitational wave background from compact binaries can give us information about the astrophysics and the distribution of the properties of the compact objects. And I take the energy density of gravitational background from binary black holes as a function of the frequency and as a function of the parameters, theta. The parameters here are going to be the mass distribution and the spin of the black holes. So it is given by that integral, where the important quantities is the energy, the rate of the energy emitted at the frequency of the source. This quantity here, which is extremely important, it gives me the rate of the mergers, and the denominator I have of the cosmology. So a couple of years back, and in 2019, what we did, we took about 20,000 models of binary black holes with different power law mass distribution and a beta distribution for their spins. And what we have found is that there's going to be a change, a difference in omega GW by almost 2 orders of magnitude, depending what is the parameters, meaning basically the mass. The spin didn't play a lot of importance, which means that when a detection of omega GW is done, once I know that there's not contamination from Schumann noise, once I know that comes from compact binaries, I come into that later on, then I can get information about the population of the compact object. Now, the next example I would like to give is a background, a stochastic now background, which is formed by cosmic strings and how I can get information about physics beyond the standard model. So the universe expands, the temperature drops, it may undergo a series of phase transitions followed by spontaneously symmetry breaking that may leave behind some kind of topological defects as a relic of the previous more symmetric phase of the universe. One of these class of effects are these one-dimensional objects, the cosmic strings. So the strings, they oscillate, they emit gravitational waves. In addition to strings, when they meet, they exchange partners, and in the position where they exchange partners, they form some discontinuity, which we call it kink. Kinks appear always in pairs, and they propagate along the string, and they can collide. In addition, since strings are relativistic objects, there are points along the string where instantaneously they move at the speed of light, and we call them cusps. Cusps, kink, and kinking collisions are points along the string where you have a lot of emission of gravitational waves. So now I should go back and do exactly what I did here for the case of where was my model here? For the omega GW from compact binaries, and I told you that the important quantities are the spins and the masses, and do the same thing for the case of the cosmic strings. Here, what is going to be important is going to be the distribution of loops, how many loops I have of a given size, which is this quantity here, how many kinks I have, how many cusps I have. These are given by a numerical simulation. So there are a couple, that is what I call model A and model B. I'm not going to go to details into that at all. So as I have the mass distribution of my black holes, here I have the loop distribution of the loops, how many loops of a given size, how many kinks, how many cusps, and these they come from complicated numerical simulations, and there is not a lot of agreement. And then once you do that, the only free quantity you have is the tension of the string. The tension of the string, it is very important here. For instance, I give a relation between the values of the tension of the string and the different energy scales. So you have an idea about when these objects were formed. And then by looking at the omega GW from our simulations, which are going to tell us what do we expect for a given model of cosmic strings, and compare it with the dawn detection coming from the stochastic LIGO Virgo search, we're able for each of these models to put constraints on the tension of the strings. For at least 3 out of these 4 models, the constraints we got are the strongest one which exist in the literature, and that means that I can go back and constrain the particle physics models that give me the formation of these objects. This goes beyond the standard model particle physics. Now, if you take into account LISA, you can put even stronger constraints, but I would like to point out that LISA, apart the instrumental noise that was taken into account, is going to have as well an astrophysical background from compact binaries, and as well a kind of contamination, if you wish, from the galactic foreground from white dwarf binaries, which means that these limits are going to be weakened by 1 or 2 orders of magnitude. Okay, so here is one of possibilities that I can get information beyond the standard model particle physics. There is another one, the first order phase transitions. So I said the universe expands, phase transitions may take place. The false vacuum is separated from the true vacuum by a barrier. So the unstable vacuum decays through bubble nucleation. After this nucleation, bubbles grow until finally they collide. And at the end of this process, they are going to convert all the Hubble volume into the new phase. During this short process, you have sources of gravitational waves, sound waves, bubble collisions, and magnetohydrodynamic turbulence. Now, what it is important is that the stochastic background that you get from this exercise is a broken power law with a peak frequency, which is mainly determined by the temperature of the first order phase transition. If the temperature is between 10 to the 7 and 10 to the 9 GeV, it is within the LIGO-Virgo capability of detection band, and this is an energy scale that is not accessible by LHC. Here, for instance, I saw the case of sound waves and bubble collisions, how you get these curves, okay, which as you can see, it can be tangent to the detectability of my instrument, and they depend on the particle physics model because they depend on the values of the strength of the first order phase transition and its inverse duration, the quantities alpha and beta. So we searched for this kind of fingerprint in the stochastic data of the 3 runs of the LIGO-Virgo, and we were able to put constraint on the contribution of the energy density from the broken power law coming from inflation and from compact binaries, because we know that compact binaries at any rate they're going to exist. Even if phase transitions are not there because they're model dependent, the compact binaries, they're going to exist. Then we took a bit of more complex phenomenological models, and we were able to put constraints in the models from bubble collision or sound waves at the temperature above 10 to the 8 GeV. And again, now I'm able to test particle physics models at an energy scale which cannot be reached at LHC. And now you can go back and take your preferable particle physics model that can give this kind of phase transition at this energy scale and constrain its free parameters. Now, I can get as well information about population 3 stars, so about early stages of my universe. So the idea here is that these population 3 stars are hypothetical kind of stars that could have been formed at early stages of the universe, which means at large redshift, and they are going to have low metallicity. So if you try to identify them, look what's happening. Here in this plot, I can see the total contribution of population 1 and 2 stars, the stars we all know, okay? And the population of the 3 star is much lower. And here you have, for instance, Einstein telescopes class 2 cosmic explorers. So there's no way you can see it. It's going to be completely washed out below the population 1 and 2 stars. So to uncover this population 3 stars, we're going to look at the residual backgrounds. And in other words, we are going to subtract individually detected major events. So as the sensitivity of our detector becomes better, and the gravitational wave interferometers can see more and more and more individual compact binary coalescence, then we expect the population 3 residual background to emerge as the dominant signal from population 1 and population 2 residual background is going to be over. And this is something that can be done. And the question is how you are looking now for that. I said before that for the compact binaries, we take the quadruple formula, you are looking with a 2/3 power spectrum. Here, this is not going to work. And this we have tested by taking this star track, which is a kind of fancy simulation of different types of, population 1, population 2, population 3 stars. The 2/3 is not going to work. Why is not to work? Because these stars have been formed very early in the universe. okay? And therefore, you see them at the merger and the ring down phases, not on the in-spiral phase. And therefore, this two-third kind of filter is not going to work. And what we have found in analysis we did like a few months back is that you can constrain these things by looking with a broken power law filter, okay? And in addition, there is a strong dependence between the peak frequency and the redshift total mass. So if I'm able to detect them, if I'm able to find their existence, then I might be able to get some information about the astrophysics of the population 3 stars. And this here, what I'm showing, it comes up from having three 3G detectors, an Einstein telescope at the Virgo site, and 2 cosmic explorers at the 2 LIGO sites. Now, a stochastic gravitational wave background from second order perturbations. Here, information about the early universe. One of the main mechanisms that can lead to a primordial black hole formation is the large curvature fluctuations which are generated during inflation. So you have that like that. The result of such an idea is that primordial black holes are going to come out by a gravitational collapse of an overdense region, which is seeded by large curvature perturbations on some small scales, once the corresponding wavelength is going to enter the horizon. Now, since curvature perturbations are coupled to tensor perturbations at the second order, then such large curvature perturbations are going to be followed up by what we call a scalar-induced gravitational wave background in the radiation-dominated era. So we're searching for some fingerprints in the all 3 observing runs of LIGO Virgo. And we didn't want to stick with a particular kind of inflationary model, so that what we did, we went to take for the curvature power spectrum a kind of log normal shape, which depends on 3 quantities. The integrated power of the peak, the width of the peak, and the position of the peak. Now, in order to be able to be within the sensitivity capability of our instruments, then we need the mass of the black holes to be smaller than about 10 to the 16 grams. So in these plots here, in these figures, I'm showing the comparison between the LIGO Virgo at 95% exclusions, as you can see here, okay? These are the solid lines, depends on the value of delta for 2 limits, in comparison with the constraints from Big Bang nucleosynthesis and CMB, okay? And the primordial black hole formation, okay? And these green shaded curves correspond to evaporation timescales. What we have found is that we can put 95% confidence upper limit on the value of this integrated power of the peak down to this value at 10 to the 17 over megaparsec. So these are the constraints that we're able to put. This actually is a paper that appeared in PRL yesterday, I believe, yesterday, yes. Now, again, let me continue about possibility of gravitational waves to give us information about the early universe. We know that we live in a universe where there is a matter over antimatter, there is this asymmetry, and that one of the Sakharov kind of criteria requires parity variolation. So early universe mechanisms can create parity variolation, which is going to lead to a production of asymmetric amounts of right and left-handed circularly polarized isotropic gravitational waves. Astrophysical sources are unlikely to give circular polarization, which means that if I'm able to detect such parity variolation, then I would know that the source is cosmological and non-astrophysical, and then I may be able to put some constraints on my model. Such studies have been done. There is a beautiful papers in Chen Simon's gravitation theorem by Yang, axiom inflation. And then what we have done ourselves, we tried to study that in the case of a turbulence in the primordial plasma for either first order phase transition or primordial magnetic fields, which are coupled to the cosmological plasma. Just for a bit of background, if we have this parity variolation, then the 2-point correlator of your strain is going to be given in terms of the Stokes parameters I and V. The V is going to be 0 if you have completely unpolarized gravitational waves. And when you go to write down the omega GW now it's going to have a contribution from the polarization degree, which can take any value between +1 and -1 for fully right or fully left polarization, and vanishes if you have an isotropic background. We searched for that kind of fingerprint in the data, and we found, first of all, we didn't find any kind of parity violation. But what was important is that we found that actually there are going to be two limits of omega GW that are going to be important. One that confirms the presence of polarization background, but another one which is to be stronger, that is going to allow us to estimate the degree of polarization. So depending on what the detectability, the detection is going to be, this may allow us to be able to deduce the value of the polarization, or just to say that there is a kind of parity violation, but we cannot estimate the value of the polarization degree. And then we applied that in the case of axiom inflation, but I'm not going to go into detail. Now, alternative theories of gravity, okay? A test of GR, if you wish. Now, if you take theories beyond GR, then as you know, there are going to be extra polarization modes, scalar and vector beyond the tensor modes. So this omega, this dimensionless quantity, is going to have extra contributions. You take the sum, okay, with different values of these factors which correspond to the ratio of the overlap reduction function, what it will be the value of this power law and so on. Now, then if you try to do that with the transient kind of events that we have, then too bad, we cannot do it. Why we cannot do it? Because we need at least a network of 6 detectors in order to uniquely determine the polarization if you have 2 vector, 2 scalar, 2 tensor modes. And badly enough, not only we have 3 detectors, but 2 of them, the LIGO detectors, have nearly the same orientation, so we cannot do it. So a few years back, we came up with a Bayesian method to detect and characterize the polarization of the gravitational wave background. This method has been used afterwards in the second, the third observing run, and the result is that there is no evidence of non-GR polarization, and the non-detection of extra polarized mode is in agreement with the predictions of general relativity. Now, let me move on. So I discussed so far a different kind of contributions to the gravitational wave background. I discussed about the case of compact binaries with the 2/3. For defects and inflation, it is flat. For a broken power law, for the case of first order phase transition. So the question is, if tomorrow you find a detection, you have a detection, you know that it's not contamination, can you tell me where the contribution comes from? So this is an interesting question and very relevant, and we tried to address that, I don't know, a couple of years or a year back or a year and a half back. So we did a Bayesian kind of search. Here is our posterior, okay, which depends on which is the parameter of the model. So in other words, this omega GW is something which I calculate given my model with its parameters, theta GW, okay? And this sigma cat is what the cross correlation which I get from the data. Okay, and then we're going to compare the models, a power law of compact binaries plus cosmic strings, a compact binaries. This I know for sure I will have it. Okay, plus broken power law, which comes from first order phase transition, and we study the Bayesian factors. Now, the network of the detectors we have considered was the 3 current detectors, the 2 LIGO and the Virgo one, with all 4 sensitivity and 1 year of running time. And the results that we have found is too bad. We are not going to be able to disentangle between the different contributions. Then we said, okay, let us go to 3G detectors, okay? And then we consider, as usually people do, is 2 cosmic explorers at the LIGO site and 1 Einstein telescope at the Virgo site. It's unclear where it's going to be, but anyway, let's take for working purposes the Virgo site, and 1 year of running time. And what we have found, that is indeed, if we have this 3G detector, we may be able to identify what is the contribution of each of the sources. But careful, there will be a very important kind of task in order to be able that. In other words, we have to somehow be able to subtract the loud astrophysical background that will be present for the 3G detector. So there's something that one has to keep in mind, that that's something that goes on in these Einstein telescope studies. Now, so far, I discussed the background, which is isotropic, like for the cosmic microwave background. Okay, here you have the beautiful plot for the CLs from the temperature fluctuations. In a similar way, if I have an anisotropic distribution of my sources, I will expect to have an anisotropy that is going to show in the maps of my sky that are not going to be the electromagnetic kind of maps, but the gravitational wave maps. And then that's an independent way in order to study large scale structure. Instead of the 2-point correlation of the temperature fluctuation, I have the 2-point correlation of the fluctuations in the omega GW. Now, there is an important kind of limitation here, is that there is the diffraction limited angular resolution on the sky. In other words, how many else multiple moments I can expect to be able easily to identify from my data. In other words, what is the minimum resolution of my object? And that will depend on the distance between the detectors and the most sensitive frequency. And that will give me the minimum resolution or the maximum value of the multiple moment L. And too bad, for the case of the compact binaries, it is down to 4. For the case of defects of inflation, it's 3, and then I go up to 16 for the case possibly of supernova. So that's not terrific for the time being. Of course, we expect with more interferometers somehow to that to become better. Anyway, so if you in the LIGO Virgo collaboration, we have been looking for such kind of anisotropies in the sky, and here is the constraint for compact binaries. Theoretical studies, they give us a constraint which is stronger by 3 orders of magnitude. Here I show you this map of the sky, which is not the electromagnetics, the gravitational wave spectrum. What is very important to keep in mind is that what I said at the beginning, that the astrophysical model is going to affect the background, the monopole, in other words, the astrophysical model is not going to affect what is the anisotropic map that I get. Now, later on, we have found that there is actually a kind of problem increasing here, as people from astrophysics would immediately have identified, that the finite number of the compact binary correlations at the short time that they spend in the band of my interferometer, they are going to contaminate my angular power spectrum by what is called a shot noise. So then we came up with a proposal that by cross-correlating different time segments, we're able to build a minimum variance unbiased estimator of the anisotropies, and this is something that is planned to be used for the 4th observing run of LIGO Virgo. Now, there is actually another thing that up to now, what I have taken into account is the intrinsic anisotropy from the anisotropic distribution of the source, the distribution of black holes or neutron stars. But there are some kind of what we call projection effects, which are going to be all the effects which intervene between the source and the observer. And the study of that we have done shows that there's going to be an important contribution to a few tenths% in the angular power spectrum, and it would be more important for large scales. And it will depend on what is the interferometer that you are taking into account. Now, a similar study for anisotropies from the anisotropic distributions of sources being here cosmic strings have been studied. And again, what is the message is that from theory, we have a stronger constraint. And it is also important to keep in mind that the particular model of the loop distribution is not going to play any effect on what is the anisotropics that I can get from cosmic strings. Now, let me move now to a kind of test of modified gravity models. Now, in general relativity, as we all know, gravitational waves, far from their source, they propagate along non-geodesics with an energy and momentum which are related by the standard dispersion relation E squared equal P squared C squared. Extensions of general relativity, modified gravity, and so on, may violate this, for instance, by giving a mass to the gravity. Okay, and therefore, what we have done to probe generalized dispersion relation, we just consider we adopted a rather phenomenological modification of the dispersion relation by adding this term with 2 phenomenological parameters, capital A with a subscript alpha and P with a subscript alpha. For instance, And that we did it for different values of A. For instance, the value of alpha equal to 3 is double spatial relativity, 2.5 multifractal space-time, and so on and so forth. So what is going to happen then is that this kind of additional phenomenological term is going to modify the phase of the strain in this way. You are going to have a frequency dependence dephasing of the gravitational wave signal, which depends on what is the luminosity distance of the binary, what is the chip mass, what is the redshift, what is the distance parameter, and so on, where the cosmology is going to enter. And as the wave propagates towards the Earth, then this dephasing is going to build up. So by taking the most recent catalogs of the transient effects, constraints on these two phenomenological parameters are put. So now you can go back to your preferred modified gravity model and constrain its free parameters. And in addition, there was a constraint on the mass of the graviton, which is about a bit less than 2 times stronger than the one you can get from the solar system bound. And by having that in mind, we put constraint of 4th order gravity non-minimally coupled to the massive scalar field. In particular, we have applied that in the case, I don't know how many of you are familiar with that, with the cosmological model, which is based on the non-commutative spectral action approach of Alain Connes and Samsonite.
Professor Sakellariadou,
yes,
you have about 2 minutes.
I have 2 minutes. So then let me speed up. I don't have much more to say, but just a couple of more things. So again, for the propagation of gravitational waves and what you can say for modified gravity models. Clearly, if you have standard general relativity, this is the equation for the propagation of gravitational waves. Here is the anisotropic term. Here I work in conformal time. Various modifications of gravity have been introduced, like Hordinsky, degenerate, higher order scalar tensor, and so on. And the propagation of gravitational waves now is going to be changed by putting the mass of the graviton. The speed of the graviton can be different from the speed of light, and this quantity here that modifies the friction term in the propagation equation. So then this is going to lead to effects in the amplitude of the gravitational waves propagating across cosmological distances, what we call the gravitational wave luminosity distance, which can be probed by LISA standard sirens. This is the standard luminosity distance CGR, and we have modeled it in a very simple way. In the case of modified gravity models, will be this parameter here, which is related to what is your preferred modified gravity models. And we were able with LISA kind of simulated catalogs to constrain this parameter to an accuracy that is about 1%. Now I need to go on briefly for quantum gravity proposals. And I don't want to say much here, but it has been constrained the number of space-time dimensions by the GW170817. For instance, some models of string theory have been ruled out by relating what's going to be the strain, which is measured to the interferometer, to the luminosity distance, which is measured from the optical counterpart of the standard siren. And these quantities here depend on what is your model of string theory. Now, you might wonder again whether proposals of quantum gravity can indeed be tested. Just give me 1 extra minute, please. Can be tested with gravitational waves. And one can naively say that this can never be the case because any kind of correction is going to be suppressed by the Planck scale. We have shown that this might not always be the case because for almost all quantum gravity proposals, there is this kind of long-range non-perturbative mechanism, which is called dimensional floor, this change of the space-time dimensionality. So we have calculated what will be the distance scaling of the amplitude of the gravitational wave radiation, which is emitted by a binary system and is observed in the local wave zone. And we have found that depends on, is the product of this dimensional function, which depends on what is the source, and the power law distance behavior, which depends on this parameter gamma. Now, we went then to find the consequences of the quantum gravity dimensional flow for the luminosity distance scaling of the gravitational waves in the frequency band of LIGO and LISA. And here, this is the luminosity distance of gravitational waves propagating in a dimensionally changing space-time in quantum gravity, and this is model independent. Now, everything here is what, again, the strain measured in the gravitational wave interferometer, the luminosity distance from the optical counterpart, and what we have seen is that in order to be able to detect such a kind of signature, if there is an electromagnetic counterpart, you need a condition between the scale at which quantum gravity effects are important and the scale at which quantum gravity effects are the dominant ones. And the only cases that this can happen, because these values exist for all kinds of quantum gravity models you want to find in the literature, the only models are group field theory, spin forms, and loop quantum gravity. This does not mean that these are the correct models of quantum gravity. This means only that these are the ones that can be tested by electromagnetic counterparts. So I should stop here. I wanted just to say something that, of course, I have no time, that dark matter will put also constraints on the axion. We could constraints on the axion with masses below 10 to the minus 11 eV by excluding the ones with this decade constants at the 3 sigma level. And this is a constraint that can be very useful for axions as light dark matter candidates. And then let me just finish with just putting my conclusions. And then I take questions. Sorry for being beyond time.
Thank you, Professor Sakellariadou, for this enlightening talk. We have time maybe for 1 or 2 quick questions. Can you raise your hands, those who have questions?
Let me stop sharing, at least.
Srinath, can I ask a question?
Sure.
Sriram here. What are the current constraints on these parity violating terms like the Chern-Simons gravity you talked about? You had briefly mentioned them.
There are constraints in that paper that I told you by Yang et al. There are constraints which are given. I can send you if you wish the paper. There are constraints, and yeah, both coming from basically coming both from transient or from gravitational or from the stochastic background. So there are constraints in the parameter, in the couplings which exist in the model. I don't know them by heart, but there are constraints which they exist. I can give you the reference to see exactly the constraints there. Yeah,
thank you.
You're welcome.
Any more questions? As we are taking the next question, may I request Akhil to share his slides?
No, we can finish the questions and then go, Srinath. I think Raghu and Sumati have questions. Raghu, go ahead, and then Sumati.
I know you couldn't expand on that, but very briefly, can you tell us how do we know more about axion physics using gravitational waves?
About axion like particle. You mean axion like a particle, not axion inflation?
Oh, it's not the QCD axion, but it's
no QCD actions. We have put constraints on the coupling that you have in the QCD axion, and we put constraints by using the last BHNS kind of constraint. Sorry, the BNS constraint. The last thing that I told you here, I don't know if I can change. If I can. Can I?
So it's black hole.
Yes.
No.
A neutron star. Binary neutron star. Binary star. If I use binary a black hole neutron star, my constraints can be even stronger. But if I have a binary neutron star, we put a constraint on QCD type of actions, because now you are going to have scalar radiation as well.
Oh, I see.
You see, scalar radiation. So this is going to give a kind of extra force, which is either attractive if the axion field value is the same on the surface of the two neutron stars, or is going to be repulsive. So if you allow me just a second, share screen. Let me share screen share. Here you can see here in this thing, this schematic plot shows the versus the time of a gravitational wave waveform, which is emitting during a binary merger. Okay, so in the presence of an axion, that's going to happen. So these arrows that you can see here indicate whether the effects of the axion is going to be to fasten or delay the merger, and therefore they are going to increase or decrease the speed. So I'm going to have a difference in the waveform. And by comparing that waveform with the data that we have, and we took the GW170817, we're able to put constraint on the decay constants for masses below 10 to the minus 11 eV. Did I answer your question?
Yes, I got it. Thanks.
Okay, so Mairi, thanks for a really nice talk.
Thank
I
you.
have lots of questions, but I will ask just one, quick one, which is that you mentioned this about the quantum gravity models.
Yes.
That the ones that admit a mesoscale. So
Yes.
this is also true of, for example, in causal sets, which has a non-locality scale, because these are non-local theories, but there's a scale at which a non-locality is dominant, but it's away from the Planck scale. And so what I'm curious is that I didn't understand the reason why that's important for this gravity wave. Yeah.
Yeah, what I said is that if we take the data that we have so far in the frequency range of LIGO, and we took simulated data of LISA, we found that in order to be able to detect, you need these two scales to be constrained in that way. This mesoscopic scale, which is the scale at which quantum gravity effects cannot be neglected, and the UV scale, which is the scale at which quantum gravity effects are the dominant ones, need a particular kind of relation. So if I go to the literature and I read for GFT, spin forms, LQC, CDT, string theory, Horava-Lipschitz gravity, I'm going to read these values. I found that the only case where this kind of constraint is satisfied is the case of GFT, spin forms, and LQG. So these are the ones that could generate a signal detectable with standard sirens in the frequency band of LIGO and LISA. This doesn't say that the others are wrong.
Oh, I see. Okay.
You see, it just says that doing these experiments, these are the ones that can be tested in this frequency band. That's all. And I insist on that because I don't want to give the wrong kind of impression that these are the correct ears or whatever. By no means, they might be wrong, but I can test them. The others, I cannot test them with this in this way. That's all I want to say.
Okay, that's great. But also, are there parameters that they could tune down to? If you don't detect them, is it a fault? I mean, it's great that you can you have something like falsifiability that is there. But would they be able to get by with changing parameters to say that?
I don't think so, because the values of these scales, I don't think that it depends on any parameters. Now, let me add something else. The fact that they can be detected, that implies that now whoever works in these three approaches has to look for realistic quantum states of geometry that give rise to such a signal. This step has not been done. So the fact that I can constrain them means nothing if I don't have the states of the geometry which lead to that signal. You see what I mean?
Yeah,
so there's still a long way to be able to say I can test these theories. I don't know, probably that's something you know better than me, whether these values of this scale gamma, it is something that can be tuned from the parameters of the theory. I don't know. I don't know.
Okay. Thank you. Thanks.
You're welcome.
Thank you, Professor Sakellariadou, for this again for this very enlightening talk.